So normally what we do is we design the loop and we add a 0 over here and 1 over s plus 2 in the normalized form, 2 over s plus 2. So it's a normalized form. So what it will do, it will kill this 0. And killing a stable 0 with a stable pole, it's not a problem. Unstable ones cannot be done like that. So overall system will be like this. This is reference, and I got a compensator system. This is output, and now this system will behave much nicer compared to the previous weird response of continuous oscillations. So normally the lead compensator, and we'll see something else as well. The PI controllers as well are uh, supported by the pre-filter. This is the pre-filter which comes before the summation point. So PI controllers as well as the lead compensator are always augmented by most of the time augmented by pre-filter because they add a zero into the loop transfer function and that zero normally messes up with the system response. And once we add this pre-filter, the response will be much nicer. Okay, so this was example 10.1. Go through this one once again, this lecture, and you'll find the sequence, the logic of why we are using the bandwidth, not some simple some other criteria to establish the settling time or whatever the requirement. Okay, so one thing, even in the previous lecture, I forgot, and it's not something very weird. Just like we're plotting this loop transfer function body over here, it's a very simple system. So we can directly k1 over s square. This is loop transfer function, right? So we can calculate the magnitude and phase of this system if k1 is 10 over j omega square, and if I put it equal to 0, 1, and I can calculate omega easily because it's a very simple system. And omega and j omega, two poles, right? So I can calculate omega corresponding to magnitude 1, and I can calculate the phase over here. Uh, and phase, we already know that is 180, right? And using the same formulation, I can calculate omega is equal to 10 log alpha, which was 7.78, 7.78, and I can calculate the magnitude corresponding to uh, this 10 log alpha. And basically, what I'm trying to say, for this type of simple problem, we don't need to plot these bodies. We can do analytical calculation easily. Similarly, for example 10.2, which we did previously, we can, that example was k over s plus 2, I guess. We can calculate the magnitude corresponding to magnitude. We can calculate the frequency corresponding to magnitude 1. Uh, and because all we need is value of k, and perhaps k was 20 or 40 or whatever k and j omega and j omega plus 2, we can easily calculate omega corresponding to 1. This is simple, omega square and omega, you can easily calculate that magnitude of this, magnitude of this, you can calculate, make it equal to 1, calculate omega. And to calculate the phase for this 10.1 example, phase is always minus 180. For 10.2 example, and the phase is tan inverse uh, j omega minus tan inverse uh, j omega over 2. Forget about this j. So 10 was, and using the omega from here, just put it over here and we'll calculate phase. And remember in the previous, we said phase is 162 in the previous example. So you, for the simple questions, you can calculate it directly rather than plotting the loop transfer function Bode. And even if you plot the loop transfer function Bode, you'll have the same similar answer, not exactly, but you'll have a very close answer even if you do it on the plot by by hand or right. So this was all about example 10.1 and lead compensator design. So I'll see you in the next lecture, and we'll discuss the lead compensator design on the root locus. Up to that time, thank you so much, and I'll see you later.